about our expert talk of today. Professor Carlos Gershenson is an empowered professor of innovation at University of New York and Binghamton in the US. He was a research professor at the UNAM, Universidad Nacional Autónoma de México, probably the most prestigious Latin American university. He was also, in the meanwhile, professor, researcher, and scholar at several prestigious institutes like the Santa Fe Institute, very renowned in terms of science, systems and science, MIT, Northeastern University, and St. Petersburg University in Russia. Currently, he serves as president of the Complex Systems Society and is editor-in-chief of Complexity Digest and member of the advisory board of Scientific American. Professor Gershenson is Mexican. He got his first degree in computer engineer and his master's in evolutionary and adaptive science in Sussex University, and his PhD at the Free University of Brussels, where he worked together with Francis Heilgen. There he produced a couple of beautiful pieces that I recommend highly on philosophy and complexity, and complexity and philosophy, which I highly recommend. Interesting through this background is that Carlos managed to keep an eye on the very academic, very scientific part of the issue on complexity of systems, together with some very applied experiences on real life issues like transport in his native, on his home in Mexico City, which I hope he managed to talk us a little bit further later on. And lately, I was impressed to hear or to read that he's also interested on artificial intelligence, on which I hope that he might share with us a couple of insights. And also, if possible, time's allowed, to talk to us a little bit on the complex systems initiative that he is leading nowadays. So the talk for today is the implications of complexity, and I open the virtual floor to Professor Carlos Gershenson, our speaker today. Please, Carlos, go ahead.
Yep. Thank you very much, Daniel, for the invitation and for organizing everything. And apologies that I had to postpone a previous date that we had agreed. So, I mean, I will feel that I'm preaching to the choir, or as we say in Mexico, preaching to the converted, because we all work with complexity, so I will not delve too much in this, but let's say just to have a common ground. I mean, we know that there are dozens of definitions and measures of complexity, but if we go to the etymology, it comes from the Latin plexus, which means intertwined. So we can say that something complex is difficult to separate. And what makes something difficult to separate is that it has relevant interactions between its elements. So we can say that the characteristic of complexity, its interactions, and the opposite of complexity would be something separable that can be studied in isolation. So there are many implications of having interactions. I mean, this is described more in the reference paper here. And these implications are practical and also conceptual or more theoretical. I will mention some of them. One is that basically it limits how much we can predict. But before that, let's just imagine a system with few interactions. And the dynamics of such systems are, let's say, easy to analyze. We usually have robustness, we have stability, which are desirable properties. However, it's difficult to have adaptation in systems with few interactions. And usually the dynamics from such systems is described as ordered. And then we have many examples of order patterns and order dynamics in nature and in artificial systems. So this would be, let's say, a clockwork universe. However, there are many systems that don't have few interactions. And then, let's say, it's difficult to predict because we have lots of feedback loops. So one change propagates through the system and then it goes back to the originating node. So we have fragility, and the dynamics that we will have are usually considered chaotic. And again, there are many examples of chaotic systems, and these have been studied thoroughly. Let's say formally, this is characterized by having sensitivity to initial conditions. And when we have, let's call them balanced interactions, which is kind of a Goldilocks approach, basically not too many, not too few, and then how many is too many, it's a very contextual question. Then we observe interesting properties like criticality, like anti-fragility, and this is where we find complexity. And again, there are many examples in natural and artificial systems of complex dynamics. And we can see complexity as a balance between too few or too many interactions. So it's easier to describe the extremes of these diagrams, because if we have too few interactions, then we can study elements in isolation, so reductionism works. If we have too many interactions, then it's easier to average, because let's say more or less change occurs at all possible scales, and then statistical approaches are sufficient. However, in between, we need more information to describe what is going on, because in some cases, or in most cases, changes will not propagate through the system, but in a few cases, the changes will propagate through the system or will be drastic. And examples of this are phenomena with scale-free distribution, like earthquakes, market crashes, and so on, where we are interested in the few outlier cases. And in order to study these systems, we basically need more information, because we cannot ignore interactions, and we cannot summarize, we cannot average. So it is not a coincidence that complex systems started being studied broadly in the 1980s, when personal computers became available. Because indeed, as Heinz Pagels noted, computers are like telescopes for complexity. Without computers, we can't really study complexity, because we need to process too much information for our little brains. And also, it's interesting to mention that the distributions that these three different, let's call them types of systems, very broadly speaking, are also very different, and also illustrates us what are the differences in these three different regimes. So in order dynamics, or with few interactions, we usually have additive processes. And these produce distributions that have a well-defined mean. So it could be Gaussian, it could be Poisson distribution, it could be gamma distribution. I mean, with slightly skews, I mean, it doesn't need to be symmetric, but basically one change doesn't propagate much. So let's say there are more or less independent changes. However, in the opposite extreme, when we have many interactions, then we have chaotic interactions. So small change propagates through the network, and then we get like white noise type of dynamics. And then there's no characteristic scale. And then in between, we have scale-free like distributions. It doesn't have to be a perfect power law. We just need multiplicative processes, so that with enough interactions, one change propagates through whole the network, and then we have multiplicative change. And this yields these distributions that don't have a well-defined mean, and that limits calculus, because the fundamental theorem of calculus requires a well-defined mean in the distribution. So the tools that we are taught in high school and university are not appropriate for dealing with complexity. And one of the implications of having interactions, let's say few interactions or a balanced set of interactions, is that our prediction is limited. I already mentioned it. The technical term for this is computational irreducibility. It means that there's no shortcut for the future. We need to go through all intermediate steps in order to know what will be future state, because information processing is necessary to go from one step to the next, and there's ridiculous amount of possible states in this system, so there's no shortcut. And another implication of having interactions is that in some cases, the state spaces will grow, meaning that we get new variables. So let's say we might lose attractors, we might gain attractors. So again, the traditional methods we use for studying dynamical systems are insufficient. And also the changes that interactions bring, because just as a reminder, in high school, we are taught that if we know the initial and boundary conditions of a system and the rules governing the system, we'll be able to predict its future. However, if we have complexity, the information produced by interactions is not in initial nor boundary conditions. So we need precisely to go through all intermediate steps, and that's precisely what gives us irreducibility, computational irreducibility. But then these interactions can also produce changes in the state space at different timescales. So, for example, in a traditional system, we have a function, and then there is change over that function, and then we can study that. But then with time, the function can change. Some parameters of the function can change, and then we need to adapt to those changes. And in some cases, we can predict which changes might be, or the space of those parameters that will change. But in some cases, we don't know beforehand how the parameters will change. And then the way in which those parameters change can also change. So we have changes at multiple temporal scales. And then, of course, we can say, well, if we have more and more information, then we just add more and more dimensions. But then the more dimensions we have, the more data we require, and our spaces become sparser and sparser. So we end up with systems that they are always visiting states that have never been before visited and will never be visited again. So again, that limits predictability because we cannot exhaustively explore all the possible states of these huge systems. And of course, there are ways on going beyond these properties of complex systems. I will go into them, but let me also mention the limits of practical computation. So theoretical computation assumes that we have infinite space and time, meaning memory and computation time. So there's this example of monkeys in typewriter, and if you give them enough time, they'll produce the complete works of Shakespeare. And that sounds possible if you have infinite time. But if you try to estimate, well, I did this with my daughter who likes theater, like back of the envelope calculation. Okay, let's not try to get the complete works of Shakespeare, just the first page of Hamlet, 500 characters. So the possible combination is 26 letters in the English alphabet, well, in the Latin alphabet used by English. 26 to the 500 is a huge number. How huge? Well, let's calculate how many of all those possible configurations the fastest supercomputer could have calculated if it were running from the beginning of our universe, meaning from the Big Bang, more than 13 billion years ago until today, fastest supercomputer exploring combinations. How many characters would we have? So you calculate those in flops, and then you get the logarithm in base 26, and the result is 17. So if we had fast supercomputer running from the Big Bang, it will get you just the first 17 characters of Hamlet. So that's never going to finish. And we end up very easily when we have models of complex systems with huge state spaces that we'll never start exploring. So, I mean, what are the alternatives that we have here? So if we have state spaces, we know that if we have complexity, meaning interactions producing information, this might grow, the dynamics might lead to changing state spaces, the combinatorics will lead to immense state spaces, we have overlaps, that's another thing that we have been studying, and it's related to artificial intelligence. If we have overlaps in datasets, then that limits our predictability. If we have correlations, then that also gives us probabilistic state spaces. And of course, we have to remember that these are descriptions, abstractions, models, not the phenomena themselves, but precisely that's how we do science. And let me mention briefly emergence, which is a common property of complex systems, perhaps most controversial one, because I mean, it already since ancient Greece, Aristotle had used the expression more that the whole is more than the sum of its parts. So that more or less refers to what we understand today as emergence. In the 19th century, British emergentism produced many interesting texts, but in the 1930s, with the success of molecular biology, in science, people started kind of ignoring emergence, or let's say the narratives that use emergence became less popular. And in the 1980s, when people started studying complex systems, it became, again, a topic of discussion, but it gained somehow a bit of ill repute because some people were saying, oh, emergence is like a measure of surprise. But then if it's a measure of surprise, first of all, it sounds objective, and we don't like subjectivity in science. And then some people would say, oh, then it's just a measure of your ignorance, because once you understand the system, you're not surprised, and then therefore there's no emergence anymore. But of course, there are many examples of emergence that are not dependent on the observer. So for example, the macroscopic properties of materials are emerging from the interactions of its components. So for example, we can know everything that there is to know about the carbon atoms, but depending on how they interact, they will produce materials with very different properties, such as graphite, diamonds, nanotubes, buckyballs, and so on, that they have different colors, different malleability, different conductivity, and so on. And there are many examples of emergence like this that are not subjective, because also many people studying emergence were relating it to consciousness, and that's problematic for different reasons. But anyway, very generally, we can describe emergence as information that is not present at one scale, but is present at another scale. And then we also have different flavors of emergence. We can speak about weak emergence, strong emergence, synchronic, diachronic, upwards, downwards. With this diagram, let me try to explain it. All of this, so synchronic occurs in space, diachronic occurs in time. Let's say we have different descriptions. Weak emergence is just without feedback. So for example, the temperature, we can say that it's an emergent property of the kinetic activity, of the kinetic energy of molecules. But then that temperature, it's something that an observer describes, and there's no feedback on the properties of molecules. However, in a society, individuals define social norms or meaning of words, and then these have feedback into the individual behavior. And this is called strong emergence. And some people have problems with it because they're reductionist, but anyway. And then depending on the scale of description, we can have upwards, downwards, or transversal emergence. But of course, here we can enter more into philosophical discussions about emergence, but let me just continue. Speak about self-organization, which is another property of complex systems. It's observed in many biological and also chemical systems where, for example, flocks of birds, there's no leader. Then there are patterns that can be observed through the interactions of the components of the system. So one notion of self-organizing system, it's where precisely global patterns of behaviors are products of interactions of the components. So we could ask, how could we organize such a system like Mexico City Metro in the rush hour? This video was taken more than 10 years ago in the ladies section. So you can see that if you want to enter the train, you need to do it through the window because there's no space to do it through the doors. And at the time where you need to transport most passengers, the lines collapse because the trains cannot leave the station, the doors cannot close, nobody gets in, nobody gets out, and it's chaos. So how can we change the behavior? It's not that people enjoy pushing each other, it's that if you don't push your way, you will never reach your destination. So it's like everybody playing a game that nobody likes to play, but if you don't play it, everybody loses. So this is the same station after an intervention we made about 10 years ago. This is the ladies section. It's the same people. We didn't import German passengers. They're the same Mexican passengers. And they have very different organizations. So it's the same elements, but very different organization. What changed? We put signals on the platform of where the doors would stand and just ask passengers, please don't block the exits. Without that information, even if you want to let people out of the train, you don't know where to stand, and then the platform gets completely blocked and nobody can go out, and it's precisely what you saw. So with this information, people entering the station don't need to look at this information because the people who are already standing, and I mean, we didn't expect that people will queue, but once people are queuing, people entering the station see that there are queues and then they just queue. So they have enough information to change the interactions, the same passengers, and then the behavior changed. So these are some simulations about the differences because we tried different approaches before doing this. We were also thinking, oh, maybe we can have some dedicated doors to enter or exit, but then this was almost as efficient and it would be difficult to implement. And then in other stations without the signals, people also change their behavior because they observe that everybody benefits from this new behavior. And let's say that has transformed and then it propagated to many stations. So this is another viral video of a different station, also rush hour. So you can see that the station is completely full, but the people are arranged in a very different way than in the first video. So using this case as analogy of many systems where we cannot change the elements, but we can change we can change the interactions between elements. The question is, what kind of mediators are necessary to change the behavior in the desired way? And of course, we can use self-organization to do this. I will mention a few examples. But for example, in Mexico, we will not change the politicians. How can we change interactions between politicians to reduce corruption, for example? will not change business people. How can we change interaction between business people to develop a sustainable economy? We won't change teachers. How can we change their interactions so that we can improve educational system, and so on. And we have applied self-organization. I mean, because here we can say that people self-organize in a different way. I mean, they were self-organizing towards a configuration that was very inefficient, and then we managed to self-organize them in a more efficient way. So we have been using self-organization to, for example, traffic light coordination. So, I mean, I will not explain the details, but traditional methods for medium densities, you get gridlocks, and for the same densities, you get maximum flow in all intersections, meaning that all intersections are being used constantly. Using simple rules and sensors, you can achieve close to optimal or optimal performance for a very broad range of densities. We were also simulating autonomous vehicles and showed that if you had to choose between autonomous vehicles and self-organizing traffic lights, the traffic lights would be would give you a higher improvement than the autonomous vehicles with dumb traffic lights. If you have both, then it's even better. But if you have to choose one, then the self-organizing traffic lights are more efficient. But of course, it's tricky because if you suddenly improve traffic for cars, then the demand of cars would increase, and then you will have higher density, and then if you have higher density, you will have very inefficient traffic flow anyway. So at the same time that one might improve traffic light coordination, one should reduce the density of vehicles at rush hours. And we also use self-organization to regulate public transportation vehicles, buses or trains or trams. So the theory tells us that if we have equal headways, meaning the time between vehicles is equal, then passengers will wait minimum time at stations. However, this configuration is unstable, so the vehicles bunch up, and then the system collapses. This is a well-known problem, and we took inspiration from anti-collision communications so that vehicles try to keep a similar distance with their neighbors, and actually the performance is better than the theoretical optimum, because even when passengers wait for a bit more time than with equal headways at stations, once they board the train, they reach their destination faster because the trains don't have to keep the same time to keep the equal headways. And also in this simulation, basically the black dots represent trains in the first metro line of Mexico City, or metro line number 1. And then when they go a bit to the right, it means that they're stopped at a station. And then there's an interruption in the service of 15 minutes. So in normal configuration, the system collapses and all the trains bunch up, and then the system doesn't recover. With the self-organizing method, since vehicles try to keep the same distance with their neighbors, the trains that are in front of the interruption, they start to slow down, so they wait for the vehicles behind. So when the system is restored, very quickly the configuration is restored, and you have quasi-equal headways. So it's quite adaptive. And with Hungarian colleagues, we have used similar approaches to regulate traffic of quadcopters, assuming that we have very high traffic of quadcopters, then you can coordinate them in an optimal way as well. And we could say that complexity implies uncertainty, which we might be averse to. because we usually want to know what the feature will be so that we can be prepared and we can take the proper measures and we can avoid undesirable situations. However, we know that when we have complexity, our predictability will be limited, and therefore we will have uncertainty. And we can see this as a problem, but we can also see it as an opportunity, because if we don't have that uncertainty, we won't have freedom. We won't have novelty. We won't have creativity. I mean, if we want to build, especially if we speak about artificial intelligence now that it's fashionable again, if we want to build creative machines, we cannot predict them because predicting novelty is an oxymoron. If we want real novelty, it has to be something that cannot be predicted. So if we lived in a universe where we could predict everything, actually we wouldn't be here, because evolution would not be possible. But actually that's already opening questions about the limits of science, and that's like a whole different talk. But Alan Turing, considered one of the fathers of computer and artificial intelligence as well, in 1948, during a lecture, he told that if a machine is expected to be infallible, it can not also be intelligent, because basically we learn from making mistakes. And since we cannot tolerate mistakes in machine, that limits how smart they can be. And we cannot have both. I mean, again, that's a different discussion, but one of the implications of complexity is precisely that we will have errors and unpredictability, but we can see this on a positive side. So just to summarize, interactions characterize complexity. This brings change at different scales, limits predictability. And I have a forthcoming book with Oxford University Press about balance, which describes this in more detail, precisely how can we reach this balance between too much change and too few change. There are many different mechanisms that nature and we can use as well. But at the end, we can see this uncertainty that we will have with complexity more as freedom rather than as a problem. So we will be hosting the conference on complex systems in October in Binghamton and online. The call for abstracts already closed, but there are some satellites which still have, I believe, open calls if you would be interested to participate. So feel free to visit the website. Also, Daniel mentioned Complexity Digest. You can subscribe to it. It's for free. It's managed by Complex System Society. And also, if you want to join the Complex System Society, we'll be happy to welcome you. So I hope there will be time for questions.
Thank you very much, Carlos. That was really an exciting tour on the complexity coming from the introduction and the framing, and visiting all these interesting aspects of it together with the practical examples. And before our colleagues queue to make us questions, maybe I can ask a couple of things in the new one, just warm up. You know, we land here, try to land this complexity and system story on real life science, on applied science. And based on that, I would like to ask you about your self-organization featuring that you used the example of the metro system in Mexico City. I guess that at some point, the users of the metro realized that queuing was more effective than just crowding. And there should be a self-reinforcing feedback loop that validated. So at the end of the day, they should realize that that's faster to queue than just to rush.
Yes.
Isn't it?
Yes. Yeah, so I say that the best rules are those that don't need enforcing. So if you need to enforce something, then that's already not so good. And you observe this with social dilemmas, where basically the best configuration for the group or the society, it's not the best for the individuals. So, for example, the same queuing mechanism. If individuals can skip a queue, they will benefit from it. So then in some places you have to put a mechanism that will prevent people from skipping the queue. It could be social, it could be physical, whatever. It could be cultural. Yeah. But then, for example, if there's no space to keep the queue, like in many places where, let's say, like in the fair, or in amusement parks, there's like these metal things that prevent that kind of guide the queuing, or like in airports, or like in banks, or even some supermarkets that kind of guide the queue. Then it's more difficult to break it, but still you have to enforce it. But then if we can come up with rules where the best configuration for the group is also the best for the individuals, then the individuals will make everything possible so that the rule gets fulfilled. And it's the case here. So once people noticed that it was efficient to organize in this way, and some passengers want to take a different approach, then the same passengers will tell them, hey, you have to queue, or we are organized like this, and then you are blocking people going out. So
if you're talking my follow-up, but is there a threshold for that? Because last year I visited Mexico City after quite about 10 years, and I've checked that this study that was used to implement these changes in Mexico City were about 10 years ago or something. Is there a limit? Is there a point? I mean, I've seen that still the marks are still in the metro, but
yes,
they were still having some issues on people boarding the metro. So is there a threshold, or is there a reinforcing mechanism that one has to use to re-educate people to keep doing the same thing? Or how would it be to make that change long-lasting, sustainable in a way?
Yes. I think that there might always be situations where people will, let's say, change their behavior for whatever reason. It's very common that if somebody breaks the rules, then that tempts others also to break the rule. And as you say, there might be a certain threshold when suddenly nobody follows rules, because so if they're not doing it, why should I do it? I think in psychology there are some studies of that approach, but in the particular case of the metro, I think it has to do with density. So from what I've heard, if there are very few passengers at the station, then people don't really put attention to these marks, because it's like, well, there's not enough people, so it doesn't matter where I stand. Everybody will get in, everybody will get out, so it's not a problem. And if somehow it gets as crowded so that, let's say, again, it's difficult to see the signs, then some people start kind of blocking the space for people going out. And it seems that in some cases, let's say, this organization is broken. I since also I haven't been in Mexico City Metro for many years. I don't know exactly what configurations are, so I can only speculate about what might be the reasons.
Thank you. Thank you very much, Carlos. Yes, I open the floor to our colleagues who want to make questions, comments. Please, Till, go ahead.
Yeah. Hello?
Yes.
Can you? Yeah, thank you so much. Very interesting talk. So my background is more on socio-ecological systems, I would say. Therefore, of course, I like this, you're saying that without complex systems, we would not be here. No,
Yep.
none of us. So I like this idea that nature is very successful because it's a very complex system. Yeah, since how many billion years? 5 billion years, maybe. Yeah. So
Yeah, I would say not only because of complexity, but because it cannot be predictable. I mean, it cannot be predictable because of complexity, but let's say we could as hope, or let's say many scientists hoped and still hope that in spite of complexity, we would be able to have perfect predictability. But then that wouldn't allow evolution.
Yeah, but I like this positive background or approach.
Yep.
Yeah.
Yep.
Of course, coming to this metro station self-organization reminded me about traffic jam, the avoidance of traffic jams in many parts of the world, where organizations or states or trying to change the behavior of individuals in a way. Also on a higher scale, I would like to ask, I mean, coming from socio-ecological system thinking, also with all the background from common pool resources from Ostrom times, etc. So I was thinking on how could your findings be transferred to higher levels, for example, environmental destruction, degradation by individuals, which collectively has absolutely negative impacts, as we know, and they know, but they do it nevertheless. So how these very strong systems of individual behavior could be changed or implemented in, taking the ideas of the background, what you just presented.
Yes. So the idea of self-organization is that one identifies different interactions, and then you identify which interactions are positive and which ones are negative. And it's a bit tautological because you put whether they're positive or negative because it's the effects on the system that will tell you whether they're positive. And then if you can find, well, we call them mediators, but it can be anything. It could be material, economic, cultural, social. If you reduce the negative interactions and promote the positive interactions, we call the negative interactions friction and the positive synergy, then naturally the system will reach a desirable state. So the difference with traditional approaches is that usually we focus on the actors of a system, like, oh, this company is polluting, oh, this government is doing whatever. And it's as we have seen recently, it's not so easy, oh, we'll get rid of that government and then everything will be fine. In Mexico, we'll get rid of the head of the cartel and then everything will be fine. But, well, somebody else will come and that's it. So how to make it hard? Well, yeah, if there's an interaction that is negative for the system, a mediator should eliminate or reduce the effect of those negative interactions. And then how to do it, it's very variable because the language I'm using is very abstract. So it will change from system to system. And in some cases, it's things that have been done already, like, oh, let's put some taxes on this, or let's put some subsidies on that to restrict or promote different approaches. But the main focus is to look at interactions rather than actors in a system. Because, yeah, if we take the approach of looking at actors, then the first temptation is like, well, let's get rid of the actors that seem to be causing trouble, that seem to be the problem. And in ecology, maybe it's tempting, oh, there's this invasive species, but how do you get rid of an invasive species? Well, you bring in another invasive species that will get rid of it. And I mean, there are all the funny examples from Australia and other places that, like with sugarcane toad and things like that. Um, so I would say, yeah, to focus more in the interactions.
Thank you.
Thank you, Carlos. Thank you, Till. Any other question? If not, I can use my chance to follow up on Till's question, because I find this comment interesting. Of course, the mediators, what you call mediators, the leverages, because a system is essentially a set of components interacting. So we should pay attention to interactions. That's where the focus should be. But what in social ecological systems, as Till labeled, what is happening now is that once a while, and now more frequently than before, emerge certain actors. And you mentioned uncertainty as an essential characteristic of complexity of complex systems. They might emerge actors with very unpredictable behavior. And it's true now that those actors might have really changing effects on the whole makeup of the system beyond what would have imagined in the past, because it's completely irrational. They are able to accumulate lots of power and to trigger changes, provoke changes that have enormous triggering effects also through the nature of the systems. I'm speaking obviously about a political system nowadays, what you maybe alluded to. What about that? To me, this scenario is something that 10 years ago never would have imagined. Somebody will rise and will change the system that we saw politically, economic, exceptionally consolidated into a real chaos as we are living now.
Yes.
What do you think about it?
Yes. So, a very interesting aspect of our times is that the number of interactions has been increasing constantly at multiple scales and at a ridiculous speed. And we can see this, for example, in epidemics. Let's say the plague, for example, in the Middle Ages, it spread through Europe throughout years because let's say, not many people traveled, and then, let's say, the fleas of rats that carry the disease would travel, let's say, relatively slow. A century ago, the so-called Spanish flu went around the world 4 times. There were 4 waves in 18 months. And SARS-1, and SARS-2, COVID-19, they went global like almost immediately, let's say in a few days. So the amount of connectivity that we have that has been increasing is having drastic effects in the stability of our system. So we know that the more interactions we have in a system, the more chaotic the dynamics become, and then predictability is almost impossible. So yeah, that's a nature of our times. And let's say we haven't developed the tools to study these systems properly. We could say it's work in progress. Probably part of that is not so much to come with a solution as we're used to, that we will solve this problem fully, but rather a way of measuring what are the limitations of the methods that we will have and ways to overcome. Just like, for example, for earthquakes, we know that we cannot predict them. But for example, in Mexico, we have this alert system. So when earthquake starts in the Pacific coast, there's an alert in Mexico City that gives you a couple of minutes to try to evacuate some buildings less than 3 stories high. And then you prepare, like, okay, there will be an earthquake, there might be a hurricane, there might be a tornado, there might be a snowstorm, and then people are prepared in spite of not knowing when the disasters might hit. Let's say they know more or less, let's say they will be better prepared, as assuming that, once it approaches, we will know with time and then we'll prepare. So because precisely we cannot predict.
Thank you very much. Thank you very much. That's a comprehensive. Of course, it's not only the connectivity, but also the virtual connectivity, the media that everybody's alluding to nowadays. Thank you very much. Colleagues, last opportunity for a question. If not, I will go my last very chance, and I really want to hear your opinion on this, is this
Yes.
one, about participation. The approach that you have exposed to us most of the time is like a top-down. You are the expert, or you have all these tools about complexity, mathematics, cybernetics, all this intellectual and academic background, mathematical background. What about participation? What we are trying to do, as Till was sketching, is that we want to tackle social ecological systems. And as you know, in social ecological systems, we have people interacting with the environment. And environment, not necessarily the ecology, but also the natural environment for us that in sometimes could be a city. That's the environment. So people determine that thing. What about involving people in the shaping of the understanding of the complexity of the system too? Is this something your lab or your team is exploring maybe?
Well, it's something essential, especially even if one comes with a solution for a community, let's say, I don't know, let's say some community has problems with drinkable water. And then if you just come and say, oh, here's your solution, in many cases they'll say, we don't need you. Not because they don't need it, but because they see it as an imposition. So from what I've perceived from colleagues who have successful projects with communities is that from the start they involve the community, and together they listen to their concerns, they listen to what they have tried, and then together they find a solution. And even if it's the same, if it end up being the same thing that you have thought that would be useful for them, the fact that you went through the process of asking them will make them feel part of the solution, and they will adopt it and they will defend it. And I mean, there's so many cases of governments that just come into a community and say, we will do this, this is what the community needs, and the community just rejects because they don't feel that they were asked, even if they would indeed be benefited. And of course, that's not the case in most cases, but I think that more generally, we lack the proper mechanisms of coordinating academia with public and private sector and with society to solve problems that it is clear that will not be solved only by government, only by academia, only by companies, or only by society. And it's not like, oh, we don't know how to do it, so we are doomed. The fact that we don't know how to do it, it kind of motivates us to keep on trying to define better collaboration and coordination approaches. And in many cases, there's the limitation that there's no general recipe, in the sense that say, okay, now we know how to coordinate, but basically you need, for each situation, you need to find again a new recipe on how it might or might not work because of all the unique circumstances that different problems face. Which, of course, for engineering, that's not what we would like, because we would like, okay, we know how to solve this problem, and then we just follow this recipe, and then we apply the recipe and we solve the problem. But then precisely with complexity, we end up with uniqueness of situations, and what was good in one place doesn't mean it will be good in other places. So again, there's uncertainty whether it will work or what should you do different. But yeah, we just have to keep on trying.